Hello again, mathletes. So this last video in our antiderivative series is going to be talking about initial value problems. It's going to be our last couple of examples here. We're actually going to be looking at the second derivative this time, and one of our examples is actually directly from physics. So let's go ahead and take a look here. So let's suppose that the differential equation we're given gives us a second derivative. Is equal, what did I pick? Okay, yeah, let's just say it's equal to 5. So we'll keep things real nice here. And it actually turns out with a second derivative, you need two initial values. You need one that has to do with the derivative. So we're told y prime of 0 is equal to 2, and y of 0 is equal to 3. Okay, so we're just going to start here. Now, keep in mind, if I'm being told that this is d squared y over dx squared, what I'm really looking at is y double prime. So y double prime is equal to 5. So what we need to find now is y prime and y. So that means we're going to have to integrate twice to get all the way up to y. So if I just do a little scratch work over here, the integral of 5 dx is equal to 5x plus a constant. Now, I'm going to call this one C1 because we're actually going to be generating another constant in the second derivative. So we're going to be able to tell these apart by their subscript. Okay, so I have 5x plus C1. Okay, now, if I want y, that means I'm going to have to integrate 5x plus c1 dx. Okay, now if we integrate that, let's see, the integral of x is x squared over 2, so that means we're going to have 5 halves x squared. And then the integral of c1 dx is going to be c1x. And then we have to add the plus a constant. This is where our second constant comes in, right? So we get a C2 there. And so we end up with 5 halves x squared. Where'd it go? There it is. Plus C1x plus C2 is equal to my y. Now, the value of these initial value problems is that we're able to find our unknown constants with these. Because if you start out with a second derivative, there's going to be a bunch of things that are unknown that could have been hidden by taking the derivatives to get there. And so that's where our initial values come in. If we know y prime is equal to 5x plus c and y prime of 0 is 2, so that's telling me when x is 0, y is 2, that means from my y prime equation over here, I get 2 is equal to 5 times 0 plus c1. Well, that goes away, and that means that c1 is equal to 2, right? So now I actually know what this is. This is now 5x plus 2. I don't have to deal with the plus c anymore. So now I know y prime exactly. Now I just need to get a hold of y. Now we know from this equation here, c1 is equal to 2, so that means the 2 is here too. So that means I can progress this a little. Oops, that's not. There we go. I can progress this a little more. Let's see, I have 5 halves x squared plus, now c1 is equal to 2, so this is now 2x plus my second constant. And this is where I actually use my initial value of y. So y of 0 is equal to 3, so that means when I plug in zeros for x, I'm going to get 3 for y. And that means that 3 is equal to 5 halves times 0 squared plus 2 times 0 plus c2, which means that c2 is equal to 3. And so I can plug in the last thing now, and now I have my solution to this differential equation. Y is equal to, I keep writing that backwards, 5 halves x squared plus 2x, and my last constant is 3, so this is now plus 3. Right? And so basically you use your initial values to plug in to figure out what your unknown constants are. Right? That's the idea of this whole thing. Now, a more practical application of this does actually come from physics. Right? If you talk about launching something up into the air, from some initial height, some projectile, it goes up and comes back down. Once that thing leaves your hand or whatever you're launching it with, it's completely subject to gravity, which means the only acceleration it's feeling is the acceleration due to gravity. So what that tells me right there, since we already know that gravity accelerates at negative 9.8 meters per second squared, that tells me that my acceleration function is equal to negative 9.8 meters per second squared. Right? So we have that right off the bat. Now, just as a reminder, if I have a position function, right, position of time, the position function, let me get this out of the way, has this relationship with velocity and acceleration, in that if I take s prime of t, I get the velocity function, and s double prime of t is the same thing as the derivative of the velocity function, is equal to my acceleration function. Right? And so what that means is that, I can get that out of there. If I take the derivative of position, I get velocity. If I take the derivative of velocity, I get acceleration. The reverse is true. If I take an antiderivative of acceleration, I get a velocity. If I take an antiderivative of velocity, I get a position. Right? So you can move both directions through this whole thing. And if I want to go from an acceleration to a velocity, I'm going to have to integrate. Now, if I'm going to be able to deal with all these constants and things like that, I need some initial values. And so what I'm going to say is that at time 0, right, so the initial time, the velocity that this thing was hurled up into the air at is v naught. And the height that it was thrown from or launched from, or however you get this thing airborne or dropped from, if there was no velocity at all, that particular height is your position. And so whatever that initial height is, s of t, s of 0, we're just going to call it s naught. Right? And so this is these are our initial conditions. Right? So the v naught and s naught would be numbers in an actual application here, but this is just working theoretically with this. So if I want the velocity, right? The velocity is the integral of acceleration. And so this means that this thing is the integral of negative 9.8 dt, which is negative 9.8 t plus some constant. I don't know what the constant is yet. Okay, so that's my velocity. So I'm going to, let's see, where can I store that here? I'm going to scoot this up a little bit, maybe right there. That way we keep everything on there. Okay, so we know a of t is equal to negative 9.8. V of t now we just found to be negative 9.8 t plus some constant. Okay. Now, over here, if we want to keep going, we found the velocity. Let's integrate one more time to find our position function. So the integral of velocity is going to be my position function, which is going to be, let's see here, the integral of t is going to be t squared over 2. So that means I have to cut the 9.8 in half. So that's negative 4.9 t squared. And then if I integrate c1, I get c1t. And then I have to generate a new constant because it's another integral, right? And so now we have our position function. So it's negative 4.9 t squared plus c1t plus c2. Okay, so we have our position function now. Now all we need to do is figure out what c1 and c2 are. So now we can invoke our initial values. And we know that, let's see, v of 0 is equal to v naught. So let's see here. So that means that v naught is equal to negative 9.8 times 0, because t is 0, plus c1. And that implies that c1 is equal to v naught. Right? So we get that right off the bat. In addition to this, our initial position over here is equal to s naught. So let's see what that does. So s naught, and this time we're using the third equation here, is equal to negative 4.9. Now t is 0 here, so that's 0 squared. Plus, now we already know that c1 is v naught times 0. So actually that's going to die. Plus c2. And that implies that c2 is equal to s naught. And if we plug all those things into our final equations, what we end up with, let me just scoot this up a little bit more, is you have a of t, which is your second derivative, is equal to negative 9.8. v of t is equal to negative 9.8t plus some initial velocity. And our position, so we can locate this at any time, is negative 4.9 t squared plus v naught t plus, let's see, c2 was s naught, so this is plus s naught. And so this actually is the equation they usually have you memorize. But you notice, if you know a little calculus, you only need to know one of those formulas, and everything else comes out on its own. So it's actually quite nice to work with it this way. It's one of the reasons I think taking physics after taking calculus or while you're taking calculus actually makes a huge difference in your understanding of the physics. So these are examples, and this brings us to the end of the video. And so, mathletes, I will see you next time, and keep your minds and pencils sharp.